Today we're going to move away from particulate matter control, and we're going to dive right into the control of volatile organic compounds, better known as VOCs. So just like we did for particulate matter, we're going to go through some of the different types of control technologies that you can use. And so today we're going to discuss thermal oxidizers. So just a quick overview of volatile organic compounds, or VOCs. When we talk about these air pollutants, one of the biggest places that we start is their sources. And so this is a graphic from 2005 from the EPA that ideally said that most of the VOCs that are released comes from either solvent use or on-road vehicles. And when we talk about VOCs and why they're so harmful, we want to move into this idea of how they get volatilized. And essentially, it's from interactions in the atmosphere. So this is a good graphic that I included where you see the traffic and industry. And so as we release VOCs into the atmospheres, they begin to migrate and move. And so they have interactions within the atmosphere, and those interactions are exacerbated from sunlight, photochemical reactions, in addition to other reactions, and then they're dispersed into the atmosphere and transported, and it has some negative effects on plant life and humans as well. Now, it's one thing to say that not all organic compounds are volatile. And so one of the biggest misnomers is methane. Methane is not a volatile organic compound, but it is an organic compound. So let's move on to control techniques. Now, before we start about some of the different equipment that we can use, it's important for us to note that the first control technique is always reduction. So that means using materials that contain low quantities of those VOC compounds, or perhaps redesigning your process to reduce the emissions from, say, industrial plants, or we're talking about solvent use, the types of solvents that you use. Now, when we talk about the equipment, there are about 5 primary types of equipments or techniques that we can use. And so today we're going to focus in on thermal oxidation. And so I'm going to let you pause and take a look at how thermal oxidation works by watching this video. And this video is included within the PowerPoint that I've posted online. So when we talk about thermal oxidation, and if you've read the video, or if you've watched the video rather, then you'll know that essentially how this process works is you have the airstream that flows in. It's literally just heated, and then once it's cooled, it's released out of the atmosphere. So we're burning off those volatile organic compounds in a controlled system at very, very high heat, and then released out. Now, in the video, it talked a lot about this process and how it requires a lot of energy. And so typically, since it requires so much energy, you see the presence of these regenerative thermal oxidizers where they're able to capture those that energy and reuse it. And so one of the things about thermal oxidizers, and a lot of times you'll hear the word incinerators, is that it has a wide range of applicability. So it can be used on almost any VOC compound, almost anywhere. It can be used for very low concentrations or very high concentrations. But the key here for thermal oxidizers is this idea of lower explosive limits. Typically, you do not use thermal oxidizers on gas streams having VOC concentrations exceeding the 25% level of your lower explosive limit. And so when I talk about lower explosive limits, what I'm talking about is that limit where an explosion can occur. And we're talking about the temperatures. And so if we're set at a particular temperature and we're at a concentration where an explosion does not occur, that's the lower explosive limit. Just right about when the explosion is occur is the lower explosive limit, and just after where the concentrations are way too high is the upper explosive limit. Now, ideally speaking, we don't want explosions in our thermal oxidizers or our incinerators, so that is the reason why they operate at 25% of the lower explosive limit. And of course, that lower explosive limit is dependent on the constituents that's within your gas stream, and so they will always range. Now, one thing to note about thermal oxidizers is this idea that since we're dealing with gas constituents of organic compounds, oftentimes what we find is that once we burn that organic compound, it releases other elements. And so common elements that's released from burning of organic compounds are chlorine, fluorine, bromine. And so what they typically do when they react with other elements within the thermal oxidizers is that they generate other chemicals like hydrochloric acid or hydrofluoride or hydrobromide. And so we can't just release these chemicals, and so what we need is another control technology, typically a scrubber, to actually remove these constituents from the gas stream. And so we'll talk about scrubbers a little later. But the next thing that I want to do is talk about designing. And when we talk about thermal oxidizers or incinerators, we focus again, since this process is so simplistic, we're just burning off the VOCs. What we're really focusing on is the destruction and removal efficiency of this equipment. And so a simple efficiency is applied, and it's just how much of the organic compounds move in subtracted from how much moves out, and it's normalized by the input and multiplied by 100. And so that's the straightforward equation when we're talking about the destruction and removal efficiency for these thermal oxidizers. And then just to give you a quick example of how we would apply this, you have a mixture described below of all of these different compounds, and it's incinerated at obviously a very high temperature of 2000 degrees Fahrenheit. And so it wants us to determine or calculate the destruction or removal efficiency for all of these specific compounds, as well as it's indicating to us that there is a reaction that produces hydrochloric acid, and so it wants us to know what's the removal efficiency of the hydrochloric acid, considering that the hydrochloric acid that's leaving is 10.7 pounds per hour. And then it also gives us the molecular weight of hydrochloric acid, as well as some of the molecular weights of the other constituents. So let's take a look at the problem. So the first thing that we want to do, very quick calculation, is to just look at the destruction and removal efficiencies. So we're using our equation of the mass flow in minus the mass flow out and normalized by the mass flow in multiplied by 100. And so what we find, and I'm just doing benzene as an example, is that once you apply the values, you get an efficiency multiplied by 100, you get that percentage. So what I've done is I've calculated all of those for the various constituents there, and it might be helpful for you to go back and confirm those values that I've included here. Now, then what we want to do to determine how much hydrochloric acid is released, what we want to do is then take a look at these chemicals. And so just from general information, and this, it will be helpful for you to read in your textbook about some of these interactions. The only constituent that can produce chlorine here is the chlorobenzene. So, when we look at the common interactions and reactions dealing with chlorobenzene and how it creates, or how it burns, heat is applied and it forms a hydrochloride molecule, then we can say that, well, let's see how much reaction is involved for the chlorobenzene. And so we take what goes in and what goes out, and for a 1 hour time span. And so when you do that, you determine that we removed in an hour nearly 1,150 pounds of the chlorobenzene. And so when you take the chlorobenzene, and this is the chemical formula for the chlorobenzene, we can determine how many moles of chlorobenzene is in this amount that has reacted and been removed. And so what we find is that 10.22 moles of chlorobenzene has reacted. And so I've just taken the molecular formula for chlorobenzene and found the mass, and then I've made the conversion. So from the stoichiometry, and so there's some information in your text, we can find that 1 mole of chlorobenzene produces 1 mole of hydrochloride. And I've been saying hydrochloric acid because this is the chemical formula for hydrochloric acid, but since it's in a gas form, we just want to kind of say chloride here. But in general, when you do a stoichiometry of this chemical reaction applying heat, what we find is that 1 mole of the chlorobenzene will create 1 mole of the hydrochloride. And so that means that if 10.22 moles of chlorobenzene is produced, 10.22 moles of hydrochloride is produced. And so then we can make a quick calculation to determine how many pounds of hydrochloride is produced from this as well, which is 372.56. Going back to our destruction and removal efficiency equation, and taking into account that we're given that the amount of hydrochloride leaving the stream is 10.7 pounds, we can then use that same equation to determine the destruction and removal efficiency. So very simple and easy and straightforward calculations associated with thermal oxidizers or incinerators and their destruction and removal efficiency. So when you go to D2L, you can find a sample problem for homework that I want you to try using the destruction and removal efficiency. If you have any questions, please feel free to reach out to me. Thanks.